Okay, so continuity we've talked about a lot, both last semester and then we've already talked about it in this unit. Um, and so what we figured out was a function is continuous at a certain point if the limit. So this actually says a couple things. It says the limit from the left, so this from the left of A is the same as from the right of A, and it equals whatever the function actually is right there. Right? That's what this says. So it implies three things. Whoops. That's from the left, that's from the right, and it's filled in. So this says three things right here. It says that the limit as x goes to a actually has to be real. So exists. And that means that each limit has to exist. The limit from the left and the limit from the right each exist and are equal. The second thing is that the function itself has to actually exist at that point. Exists. And then the third thing is that those two guys are equal, right? The limit as x goes to a of f of x and f of a are equal to each other. That's kind of the duh one, right? And so again, what that means is as x goes to a from the left, you get some value. As x goes to a from the right, you're supposed to get the same value. And that when you plug in the actual value at a, you get the value that you want to fill in that hole. Okay, so that makes it continuous. All right, so let's look at this intermediate value theorem for functions. The intermediate value theorem says that f is a continuous function everywhere from a to b. And it might be continuous elsewhere too. It might have gaps elsewhere, but all we care about is from a to b. If it's continuous from a to b, then you have to have some height at a, and you have to have some other height at b here, right? And if it's continuous from a to b, then it's got to hit every single height in between those two as well. So it doesn't tell you when it hits those values. It just tells you that it does hit those values. So like here's, if you kind of picture it, it's saying I've got some a here and some b here, and I know that I have a certain height when I plug in a, and I have some other height when I plug in b, and I know that the function is continuous everywhere from a to b. So there's no way for me to get from a to b without hitting all of the values in between f of a and f of b. That's what this is saying. Okay? It doesn't mean that I might not get extra values too. Like in this last one that I drew right here, I got some values that weren't between f of a and f of b here and here. But I still got every value between f and a and f of b. That's what this is saying, that you're guaranteed to get all of these values no matter what. So one of the ideas that you can pull from this is there's got to be a solution to this between x equals 1 and x equals 2. It doesn't tell you where the solution is. You're just trying to show that one exists. Okay? So the way that we're going to do it, we're going to call that function f of x. And we know that f is a polynomial. And we know that polynomials are continuous everywhere. Okay, and so let's just see what f of 1 equals here. So f of 1 is 4 times 1 minus 6 times 1 squared plus 3 times 1 minus 2, and that comes out to be -1. And if we look at f of 2, then we get 4 times 2 cubed, which is 8, minus 6 times 2 squared, which is 4, plus 3 times 2, whoops, times 2, minus 2. So let's see what that's 32 minus 24 plus 6 minus 2. Wait, 32 minus 24, 8. Negative 8. No, 8 plus 6, 4. Am I doing something wrong? Let's see. 32 minus 24 plus 6 minus 2. So 32 minus 24 is 8. 14 minus 2, 12. There we go. Sorry, that took a while. Okay, so let me erase this picture. So what we have is, at 1, I have a value of negative 1. And at 2, I have a value of 12. So the question is, am I guaranteed that somewhere f has to be 0? Because that's what I'm trying to show. And since it's continuous, yeah, no matter how I want to connect this dot to this dot, I'm going to have to cross that x-axis at some point. So this guarantee, so what we would write here as a justification, right, is this. Let me move this out of the way. So the justification would be, since f is continuous, and we only care about from 1 to 2, right? And f is less than 0 at x equals 1, and f is greater than 0 at x equals 2. F has to be, must be, equal to 0 somewhere between 1 and 2. X equals 1 and x equals 2. Right? And the reason for that is because it's continuous, and that's what the intermediate value theorem for functions says. Because of the intermediate value theorem for functions. Okay. Another thing that comes up, continuity just from the right or from the left, you have to modify the definition that's up here. Continuity from the right or the left, that actually means that you have an endpoint that you're looking at, right? So it'd be continuous from the left side if that dot's filled in right there, and that's an endpoint. So then you would just alter it so that it says this instead, and that, and that. If you're saying from the right, you just do plus versions instead, and that's all there is to it. Whoop. Okay. One other thing, we learned the term continuous function last year, and that referred to any function that's continuous on its domain. Okay, so that actually means functions that we studied like tan of x. That's like tan x. Okay, remember tan x has asymptotes all over the place, and it does this sort of thing every time. Well, tan x is still considered a continuous function because the domain of tan x is x can't be pi over 2 plus pi k, where k is an integer. That's the domain of tan. Well, that's the only place where you have discontinuities. Tan is continuous everywhere except points not in its domain. Not in its domain. So since it's continuous everywhere on its domain, you'd say tan x is a continuous function. Okay. And then we have, so there are other functions that we know that are continuous everywhere in their domains. So polynomials are all continuous on their domains. Rational functions, those are the ones like 3x squared plus 2x over 4x plus 1. Those are continuous everywhere in their domain. Radical functions like square root of whatever, you know, x squared plus 2x. Those are continuous on their domains. Trig functions, continuous on the domain. Inverse trig also, exponentials, logs, and then this is the key right here. Any combination that you want to make of these guys will be continuous on its domain too. So like if I had 3x plus e to the negative x and I took the sine of that all over 4 absolute value of x minus tan inverse x squared. That's really just me plugging a whole bunch of these versions of equations into each other. So since each component here, each individual thing is a continuous function altogether, this is a continuous function as well. And remember, it doesn't mean it's continuous everywhere. It just means it's continuous on whatever its domain is. Okay, hope that helps a little bit.